This is a lesson on trig identities. And this is pretty much an algebraic section, so unlike the graphing that we were doing earlier. And trig identities are equations that are always true no matter what value, what number you put in for the variable. In fact, identities are not strictly a trig concept. They're equations that are just generally always true, no matter what you plug in for the substitute in for the x or whatever variable. But the ones we look at are strictly trigonometric ones. And today I'm going to cover 8 specific identities, although there will be a few more to follow. And before we formalize all that, let's take a look at one we've seen before. Cosecant theta is equal to 1 over sine theta. We have worked with this, and we just thought of this as being a reciprocal relationship, which it is. But we also would call this a trig identity because it doesn't matter what value, what angle you put in for theta, this statement is always true. That's with the exception of where the denominator is equal to 0. Because sine theta cannot be equal to 0 because you cannot have the 0 on the denominator. We are restricted by that. But otherwise it is true for every value that you plug in for theta. So therefore it is an identity. They are used to solve equations and then also to prove additional identities. And we'll do both. We've already solved lots of equations, but here we'll make them more complex because they will require the use of identities. So I'll begin with what are called the reciprocal identities. These are not new. We've seen these before. They are on your formula sheet. The first one is cosecant theta is equal to 1 over sine theta. Now I'm arbitrarily numbering these. I'm calling this one number 1. In fact, there is no numbering system attached to them at all. And as before, we could note that sine theta cannot be equal to 0. The second one, secant theta is equal to 1 over cos theta. Same restriction, pretty much. Cos theta cannot be equal to 0. The third one, cotangent theta is equal to 1 over tan theta. Always true except where tan theta equals 0. So nothing really new there. The next 2 identities are called the quotient identities. Quotient means division, so these ones are based on the division of existing trig functions. So to begin with, tan theta is equal to sine theta over cos theta. And here too I'll keep the numbering system alive. Now this is always true, and if off to the side we can look at a very simple proof of this. Tan theta is equal to sine theta over cos theta. If you were to make the substitutions, tan theta, thinking back to earlier the unit, is equal to y over x. Sine theta is y over r. Cos theta is x over r. If you cleaned up that complex fraction on the right, that is y over r divided by x over r, you would get the r's canceling, and you would get y over x. So you'd end up with a true statement. So that verifies that that identity is true. In fact, it doesn't matter what number you put in, what angle you put in for theta, you would always get this to be the case. The next one, not surprisingly, is just the reciprocal of that, because tan and cotangent are reciprocal. So cotangent theta is equal to cos theta over sine theta. The next 3 are what often are referred to as the Pythagorean identities. And these ones are based or derived from x squared plus y squared is equal to r squared, which you will recall is the trig version of a squared plus b squared equals c squared. Now, it occurred to somebody a long time ago that if you took this basic relationship and then divided each of the terms by r squared, mathematically you're okay, right? Because you're dividing every term by the same variable, assuming r is not equal to 0, that is. And then you get this, x squared over r squared plus y squared over r squared is equal to r squared over r squared. Now r squared over r squared is just 1, of course. But the other ones, if we wrote them in this form, x over r squared plus y over r squared, you might recognize that x over r is actually equal to cos. Y over r is equal to sine. So this statement is always going to be true. The cos of an angle squared plus the sine of the same angle squared will be equal to 1. Now, that's the way it's given to you on your formula sheet and the way most people think of it, or it could actually have been sine squared plus cos squared, which would be the same thing. But this can be manipulated, and it may suit your purposes shortly to express this in terms of, say, sine squared. So if you isolated sine squared, you would get 1 minus cos squared. So you subtract both sides by cos squared. So this is equally true, just taking the same relationship and isolating one of the variables. And then, of course, this would be true as well. 1 minus sine squared would be equal to cos squared if you isolated the cos squared. Do not take the square root of them. Normally you wouldn't do that. Keep it in this form. The next Pythagorean identity is found by starting with this, but instead of dividing by r, we divide each term by x squared, which gives us this, x squared over x squared, 1, plus y squared over x squared is equal to r squared over x squared. Now, if we went further with the simplification, of course we get 1 for the first term, and then that's y over x all squared. Now, if you think back, you'll note that y over x is equal to tan squared when you square it. And then r over x would be, okay, be careful, x over r is cos, so this is the reciprocal of cos, so that's secant squared. So we end up with 1 plus tan squared theta is equal to secant squared theta. And that's the next identity. Writing it out like that. So 1 plus tan squared theta is equal to secant squared theta. And once again, you can manipulate this. So if you isolated the tan squared theta, you'd get that tan squared theta is equal to secant squared theta minus 1. Isolate the 1, and we get 1 is equal to secant squared theta minus tan squared theta. Not common that you would want to do that, but it is technically true. There's one more identity, and this one won't shock you, because we now just take this expression, this equation, and divide everything by y squared. So x squared over y squared plus y squared over y squared is equal to r squared over y squared. Now the y squared over y squared, of course, is 1, but x squared over y squared, you might note that that's the reciprocal of tan, that's cotangent squared theta. And then the far right, on the right side of the equation, r squared over y squared, well, y over r is sine, so this must be the reciprocal of sine. So we would get cotangent squared theta plus 1 is equal to cosecant squared theta. This is the last of the Pythagorean identities, the last of the 8 that we use a lot and that we'll be working with in the next little while. You could isolate the 1, or you could isolate the cotangent squared theta. So that's equal to cosecant squared theta minus 1. And then 1 would be equal to cosecant squared theta minus cotangent squared theta, should you be inclined to do that. I don't know why you would, but you could. These 8 are given to you. Do not really make an effort to memorize them. You will probably have everything but the last 2 Pythagorean ones down after working with them a little bit, but they're always there available to you, so don't, stress yourself out over it. Just keep the identities in front of you as you're working. Now, a type of question you'll get frequently is a verification. And a verification of an identity is not to be confused with a proof, which we get into more of later. A verification is where you just demonstrate that the identity is true for a specific angle value. So in other words, you substitute in the given angle, and then you see, do I get a true statement at the end of it, or do I not? So let's verify a handful of these. So number 1, the identity is cos squared theta plus sine squared theta is equal to 1. And we want to verify it for the value of theta is equal to pi over 6. So we're going back to those exact values, the rads and the degrees, which we haven't seen that much in the graphing section. Pi over 6 is 30 degrees. But I'm going to plug it in as in rad mode. Now some of you will just push this through your calculator and you'll get it demonstrated right there. And unless the question states that you should work it out in terms of exact values, then there's no reason why not. But for practice, I'll use exact values. So the left side of that equation would after you substitute pi over 6 in, would look like this. The cos of pi over 6 squared plus the sine of pi over 6 squared. The right side is just equal to 1, so I'll just carry that one down, seeing as there's no simplification required. And then the cos of pi over 6, if you think back to your special angles, or you look up at your unit circle, you might remember that's equal to root 3 over 2, all squared. Sine of pi over 6 is just 1/2. If you square those two terms out separately, root 3 over 2 squared is 3 over 4, and then 1/2 squared is 1 over 4. So that is equal to 1, and then carry the right side down, 1 is 1. So we can consider this verified. We have it. Let's take a look at another one. These questions are more than anything practice with exact values. We actually know that these statements, these equations are true. So it's really not serving any real purpose other than to practice any of those. So we plug in pi over 4, 45 degrees into both. So in the left side, we would get 1 plus tan of pi over 4 squared. On the right side, we would get secant of pi over 4 all squared. Now don't forget, and I've got this illustrated here, that secant is really equal to 1 over cos. So to evaluate this one, you would either go 1 divided by cos of pi over 4 squared, or you would just flip over whatever the cos of pi over 4 is. We get lucky in the tan, because the tan of 45 degrees or pi over 4, you might recall, is 1. So this just becomes 1 plus 1 squared. Now the secant of pi over 4, the cos of pi over 4 is root 2 over 2. So all I did was I flipped over that root 2 over 2, giving me 2 over root 2, and then we squared. Now you might be a little rusty in these if you haven't done them for a week or so, but that's how they work. And then we're there. 1 plus 1 squared is 1 plus 1 is 2, and then 2 over root 2 all squared is 4 over 2. Root 2 squared is 2, and so 2 is equal to 2. So shockingly, it is a true statement. Let's do one more. This one's a little different because it doesn't have an exact value. It just has an approximation, 2.4 rads. And this makes it easier for us because we really don't have any choice. We just have to push it through the calculator. So if it is decimalized like that, you have to use your calculator. Otherwise, you have an option with it. So let's simplify the left side down, and the same with the right side. Cotangent squared theta is 1 over tan, in this case 2.4 squared, plus 1. Now I'm in rad mode and everything, but you're probably thinking, why can't I write that as cos squared over sine squared? The answer is you can. It's just that I chose to do cotangent as 1 over tan, because cotangent it'd be okay to do it both ways. And then the right side, cosecant squared theta, would be 1 over sine theta squared. So when you push it through, 1 divided by tan of 2.4 all squared, make sure you close that bracket, then plus 1 will give you 2.1918 to 4 decimal. And then the right side, 1 divided by the sine of 2.4 close bracket squared would give you 2.1918. So we did it. This thing is verified even for this more awkward value. The next lesson will include some proofs and things of these, but this is a start, an introduction to these identities and also a few verification questions. But keep your formula sheet or these identities in front of you. Thank you for your time.